Welcome back to the Moldex3D Advanced Tips and Tricks. My name is Alex Baker, and today we're going to be going over optimizing cycle time using simulation. In this lesson, you can expect to learn about evaluating the balance between shear heating and cooling, determine the gate freeze time in your packing stage, and recognize the cooling time required to eject the part from the mold.
When we're talking about cycle time, there are four main sections that we can optimize. There is the filling time, there's the packing time, there's the cooling time, and the time between cycles. So we have the filling, packing, cooling, and what we call the mold open stage. The mold open stage is a little bit tricky to optimize. It's more from a physical side, how long it actually takes to eject the part and for the part to fall into the bin. So we're going to leave that out of this discussion. We're going to optimize the filling, packing, and cooling. Most of the time when I'm looking at optimizing any sort of process for anybody, I will first look at the cooling, because the cooling takes up the largest chunk of the cycle time pie, if you will. If everything were converted to percentages, the cooling time would take up the largest chunk of that pie. But that's not to say we can't optimize all of the other three, or I should say the other two components. So the filling, packing, and cooling can all be optimized. The way to optimize the filling stage is really by identifying how the filling time can be calculated. So when we're talking about the filling stage, we're really the controlling factor is velocity or flow rate. So flow rate in, let's say, cc's per second is going to be equal to the volume that you're trying to inject divided by the filling time. And that should be pretty simple. Everybody should be able to pretty easily comprehend that. We're just taking the amount of volume that we're injecting divided by the amount of time that we're trying to inject in gives us our initial flow rate. That's how Moldex3D works. So that's how our initial flow rate is calculated in Moldex3D. But you might say, how do I get this filling time? What should I use for a filling time to optimize my injection cycle? So we have this. We have a second equation that we can use. Filling time, or injection time, whatever you want to call it, in seconds, is going to be equal to the max flow length divided by the injection speed. And this would just be your machine's injection speed. And you might say, Alex, that doesn't help me at all because I don't know what my injection speed actually is. So the injection speed is kind of a tricky subject. Most of the time you really won't have the machine specified when you're running simulation. The whole purpose of the simulation is to tell your molders what to use for their inputs, not necessarily the other way around. Now, there are definitely correlation studies that you can do, or preemptive studies that you can do where you actually know what machine you're going to be using, but sometimes you don't really know that. And for that reason, the injection speed can be set for most machines, can be anywhere between 100 to 150 millimeters per second. That's usually where most machines lie. If you don't know what machine you're using, like I mentioned earlier, then you can use 120 millimeters per second for this equation. All right, so that actually makes this equation very simplistic. All we have to do is calculate our maximum flow length, which will just be the distance from our gate, or the place that we're trying to gate, all the way out to the end of fill. I can use my tool, measure distance, to obtain that distance, and I can actually do this before I run the simulation. I don't necessarily have to have any simulation results to obtain this information. I can just go from a point near my gate to any point at the end of fill, and then the distance will be calculated here. So in this case, I have about 200 millimeters from my gate to my end of fill over here. I could do the same thing for the opposite direction as well. So I want to be able to figure out what my maximum flow length is. And once I do that, I can satisfy this equation and calculate what filling time I should use. Now you'll actually see that when you go and set up your analysis for the first time, or when you just mesh your part and go to select the process, the default filling time will follow this rule pretty well. And that's our HQ has coded the default process such that it actually follows this rule almost exactly. There's actually a couple more optimizations that are made, such as like going around curves and things like that. But for the most part, this equation is almost exactly what we use for our defaults. And that's what makes our default process so trustworthy, which is kind of cool. So that's how you can optimize your filling time before you run the simulation, but after you run the simulation, there's also more optimizations that you can do. So just looking at my filling results, honestly, the filling time doesn't really tell me anything. So the filling time just tells me how much filling time I actually input into the simulation. In this case, it was about 2 seconds. But what we see here, the result that I always go to check whether my filling time is appropriate or not, is the temperature result. The temperature result is probably the best way to determine whether or not I'm filling my part too fast. It unfortunately won't tell you if you're molding too slow, but it will tell you if you're molding too fast, which seems kind of counterintuitive because we're really trying to optimize our cycle time, meaning we're trying to reduce our cycle time. But through the temperature result, we'll be able to tell whether we need to increase our cycle time or not. So through the temperature result, the biggest thing I'm going to look for is shear heating. So shear heating is going to be a consequence of how fast I'm moving my material. So the amount of friction that occurs from my melt or from my viscous flow to my stationary mold plate or my stationary mold base, that's what's going to cause the temperature to increase over the duration of flow. Now, there's two competing effects that are going on here. There's the cooling effect, which is essentially our heating source is at our melt entrance. As we move away from this heating source, we should decrease in temperature. But that's combated by the shear effect, which is trying to, the friction effect that's trying to heat up our melt. So whichever of those effects are more dominant tells us which way we need to slide our filling time. In this case, this is actually a really good case to demonstrate a bad processing time. Through the temperature result, I can really get an idea of where my hot material is located. If my hot material is located at my gate, that means the cooling effect dominated. If my hot material is at my end of fill, that means the friction effect dominated or the shear effect dominated. So we can actually tell where the hot material is pretty easily through results. I'm going to go to the result tab. I'm going to go to my isosurface function. Now, anybody who has joined our 3-day training knows this very well. I explain this in a huge amount of detail in our regular 3-day training. But essentially, we're just going to slide this isosurface, this little slider up here. We're going to move this all the way, not necessarily all the way, but very close to the maximum. And that'll tell us where the hottest material in our part is located. So if the hottest material is at the end of fill, like I mentioned, our filling time is too short. If our hottest material is around our gate, that means that we're filling too slowly. So ultimately, in an ideal world, we would be able to get the temperature to balance completely throughout the part. And when we're looking at warpage, whenever we're talking about analyzing the final part that comes out of the mold, the shrinkage discrepancy across the part or the shrinkage variance across the part is where warpage originates from. And the temperature differences, especially in the thickness of the part, is going to play a huge factor in the shrinkage variance across the different regions of my part. So when I'm looking at this temperature result, I can really get a feel for how balanced those two factors are. If I can balance perfectly between the cooling effect and the shear effect, then that means that my temperature is going to be more or less evenly distributed throughout my part. That means the shrinkage is going to be pretty even, which means that I'm not going to get a lot of warpage. I'm just going to end up with a smaller part than what we originally molded. So that's one of the most important effects that I can tell you is, look at the temperature and evaluate which effect is dominating. Are we looking at a cooling effect dominating, or is the shear effect dominating because we're filling too quickly? Now, unfortunately, the filling stage takes up probably the smallest part of the cycle time pie. So any optimizations you can make here are great, but you can usually optimize a little bit better in the other stages of your cycle. So for example, in the packing stage, I'm going to go over to my packing results now, and I'll exit out of my ISO service function. During the packing stage, we're talking, our part has been completely filled. We just need to know how much time we need to apply pressure in order for the shrinkage across our part to be nice and even. The whole purpose of the packing stage is to reduce the shrinkage in our part to make it a little bit more dimensionally stable. But how long do we actually hold that pressure for? That's the optimization that we're going to make here. All right, and the optimization is always going to be based on how the ability of the material to distribute throughout the part after the part has been filled completely. So the only material that can move in the packing stage is material that's above the freeze temperature. So any molten material is able to distribute pressure, and that distribution of pressure is going to allow the packing effect to continue. Once that material freezes, we're no longer able to distribute that packing effect to the rest of the part. And the way we evaluate that, and the one result that we can use to evaluate our packing time, is the molten core result. So the molten core result tells us how much of our material is frozen versus how much of the material is still molten. The blue material you see here is molten, everything else is frozen. So we can see that in this case, right at the end of our packing stage, that's what I'm looking at right now, it's the end of packing. And you can actually look at your the information tree here. You can look at the information tree to see what the process was for this. You can actually see that the molten material is concentrated around the gate. And that really, even though my gate isn't frozen necessarily, and we're going to look at gate freeze in a few moments, but even though the gate isn't frozen directly, the material around the gate is actually frozen. So a lot of people have come to me and say, can I use the gate freeze estimator from the computation time or from the computation parameters to estimate where my cycle time? And my answer to that is simply no. You cannot use that to directly tell when your gate freezes, because the material around your gate may be frozen off from the rest of your part. If I continue to pack out my material, or if I continue to apply pressure, that material is only going to be packed into this region. I'm going to pack out this volume insanely well, but not the rest of my part. So I'm going to get a really low shrinkage around my gate, but the rest of my part is still going to be at a relatively high shrinkage. I was mentioning that the shrinkage variance across our part is going to cause warpage. So not only from a temperature standpoint can we get a variance in shrinkage, we can also get a variance in shrinkage from the pressure distribution as well. These two factors both play into the final warpage that we're going to get out of the part. So not only can we use this process to optimize our cycle time, increasing our production efficiency, but we can also use this process to evaluate what the cycle time is doing to our final part. Now, what I can do with this is I can actually go back in time in the cycle to figure out when this gate is no longer, I'll say, isolated. I won't say frozen, because the gate itself, there's no disconnect here, which again we'll be getting to in a few moments. But I'll say when the gate became isolated is really what we want to figure out to optimize our packing time here. So what I'm going to do is right-click on the packing header, and you'll see that there's a bunch of what we call time steps, or times before the end of packing, that we can go to. So for example, I'm just going to go to the last time step here. I believe the time step that we were just looking at was about 9.5 seconds, if I remember correctly. This one here is going to be at 8 seconds. So you can actually see that the material is completely molten throughout the part. And this can be a little bit tricky sometimes because we do want to be able to pack out the part effectively, but we don't want to pack out the part in a single location. So for example, in this case here, when we're at 8 seconds, we're able to distribute the pressures. So we actually do want to continue to pack out our part. We don't necessarily want to end at 8 seconds. We want to end once this gate becomes isolated. And that's where your time step numbers, the amount of time steps that you have, is going to come into play. So the number of time steps that you have will allow you to get better resolution for figuring out what packing time you need to use for the simulation, or really for the real molded part, ultimately. So the more time steps you have, the better you're going to be able to conclude when your packing stage is over with. All right, so to increase the number of time steps, I know that I get this question quite a lot. How do I increase the number of time steps out of the simulation? And the way to do so is simply through the computation parameters, packing, edit, and I usually use 10. That's usually enough resolution where I can make some sort of reasonable conclusion, but you can always use more. The thing to be wary of is that the number of time steps that you use is going to impact your computation time slightly. Usually time steps take anywhere between 20 and 40 seconds to export. So if you were to use the maximum, which I believe is 99, that would add, it can add a significant amount of time to your simulation just because you're exporting these results so constantly. So you don't want to use too high. I usually use anywhere between 10 and 20. That would be my recommendation here. But you can see for this simulation, we only used 5, and that was not enough. One last thing, I also get a lot of questions about this. How do I make this computation parameter settings more consistent? And you can actually save these parameters as your defaults. So rather than having to come in here every time and change the number of time steps, you can set it one time, and then come down to this template settings, and then check the save current setting as default, and then you would press OK. And that would just allow you to always have a consistent computation parameter set. All right, the other factor that I want to look at is gate freeze. And this is another tactic that is very commonly used to correlate the process that we're seeing in Moldex3D versus the process that we're seeing in reality. So in reality, a gate freeze study is done by injecting parts at different times, or injecting parts 4 different times, and then measuring the weights of the part. Once the weight of the part stops increasing, that means our gate has frozen and there's no more material entering into the part. We can do a very similar thing in Moldex3D because Moldex calculates over time the part weight. So if I go all the way down to the bottom of my packing results here, I can go to part weight, and we can see that over time, this is actually from the beginning of our cycle. So this first 2 seconds or so is just my filling stage. But you can actually see that my part weight continues to increase throughout my packing stage. Eventually, at the end of my packing stage, which is where this dotted line is, you can see that it eventually stabilizes and doesn't change too much. And that's a way that you can more directly interpret what your final cycle time should look like. And there's actually a tactic that we very commonly use to figure out what time we should be saying that the packing is no longer effective. This graph alone, unfortunately, doesn't do a whole lot for us. Because it shows us the values, but they're always going to be constantly changing. And the reason for that is there's a feedback loop between the pressure that we're exerting onto the material in the part and the pressure that the material in the part is exerting back onto the material that we're applying pressure to originally. So there can actually be a negative flow rate. You'll actually see, or a negative part weight, for example, a negative part weight change. You can see that there's a little bit of a dip here. And this sort of dip would happen because the material in the part is actually going back into our runner system. And that's actually something that physically happens. The material isn't on a one-way street. It can actually back pressure back into the runner system, and that's where we see some very interesting things happen. So ultimately, what I want to do is figure out where this curve, where the slope of this curve goes to zero. Eventually, you can see that the slope of this curve is pretty constant, and then we get into the packing stage and it's again kind of constant, but eventually it's going to flatten out to where there's little to no change across this graph. And this is actually very easy. You might have to recall some of your mathematics from schooling, but we can take the derivative of this curve, and the derivative will tell us what the slope is at different regions. So once the slope goes to zero, that's where my packing time should end. So rather than looking at the curve, I can actually export this curve as an Excel file, and then the Excel has a nice little function that we can use, or really kind of a method that we can use to take the derivative of this curve. So I'm going to go to Result, and the way to export this information is through the History button. So right next to the ISO service that we just used previously is the History button. And since we're already looking at the part weight graph, you can see that it's already kind of loaded the part weight into the right side here. If there's nothing over here, then you can simply just check the part weight and use this little arrows here to shoot it over to the right side. And at the bottom right corner here, instead of just kind of graphing this, I can use this function to graph multiple things on the same axes. But that's not what I'm trying to do. I am trying to export this information to a CSV file. So a CSV file is essentially just a makeshift Excel format. So I can use the CSV file and save it. The default save location will be in the report folder of the project that we're currently looking at. I'm going to check the box that says open the file automatically after saving. That will allow me to just open up Excel automatically rather than having to go and find that function. Okay, so we now get the graph of our part weight. So we see the X is the first column, Y is the second column, nothing too complicated there. And what I'm going to do is essentially just take the derivative, which is, I think there's a function that can actually do this. I'm going to take the difference in Y divided by the difference in X. So I'll take this minus this, in parentheses, divided by this minus this. That'll give us the derivative, and I can just basically take this down all the way down to the end. All right, and we want to figure out where the slope goes to zero. So you can see that initially the slope is somewhere up in the 50 to 60 range, 70, and then eventually, once we get into the packing stage, you can see that there's a very quick transition. Don't be afraid if you see us divide by zero. It just means that the filling time or the X value didn't change. That's okay. But we want to figure out where the value goes to very small. So you can see that it transitions very quickly from a 0.6 here to a 0.05. That's a tenfold difference, or more than a tenfold difference. And that is pretty much where I would say our packing time should end. So rather than using your time steps, you could actually just export the part weight file and take the derivative of that part weight file to get you your exact packing time you should be using. So this is probably the most effective way, the most direct way, and the most correlatable way to reality to figure out where your packing time should be ending. Now, moving on to the cooling stage, there's a lot of time that we can save in the cooling stage. The best way to determine whether your cooling time is appropriate obviously I'm going to go to my cooling results. The result that I'm going to use is the time to reach ejection temperature. I can't emphasize enough how important this result is, because it tells us how much of our material is frozen, or I shouldn't say frozen, because this result actually shows beyond frozen. We go down to the ejection temperature. I can look at my information tree to see what that ejection temperature looks like. The ejection temperature in this case is 120 degrees, whereas I believe the freeze temperature, I have to go back to the material file, but I believe the freeze temperature is about 150. So usually the ejection temperature is about 20 to 30 degrees below the freeze temperature. So the material is already frozen, but it's not yet in an, or material that is at the freeze temperature is not in an ejectable state. Usually there's either material right inside that is not frozen. This ejection temperature is more of just I consider it like a safety factor to make sure that the material inside the frozen layer is also down to a sufficient temperature. So what we're looking at here, you can see that the color scale is actually, the units are in seconds. So this actually tells us how much of the volume of our part is at the ejection temperature at a particular time. And that gives us a lot of information. The extremes of the scale, you can see the bottom is near 0, so I won't mention that too much, but the top of the scale says 60 seconds. And you might freak out. You might say, oh my God, I have to use a minute to cool this down. And the answer is absolutely not. The time to reach ejection temperature runs until the final element in your part gets down to the ejection temperature. So that could be in an extremely hot region. That could be in a hot spot in your mold. There are a lot of reasons why the ejection temperature maximum here is much higher than the cycle time that we're going to end up using. All right, so what did we end up using for our cycle time? We ended up using 5 seconds. So 5 seconds was our input to the cycle, or input to the simulation. But you can see that even though we set 5 seconds for our cooling time, the time to reach ejection temperature shows all the way until the final element has cooled down. So that's what you can expect to get out of this result. It kind of ignores this result specifically, the other results in your cooling, things like your cooling temperature, heat flux, your cooling efficiency, all this stuff, honors the original cooling time that you input. But this result specifically ignores that initial input and tells us the information until the final element has reached the ejection temperature. So what can we do with this result? So that it looks like the entire part is blue, which tells me that the ejection temperature should be, or the time to reach ejection temperature should be 0. And that is definitely not the correct conclusion that I see a lot of people make from this result. You look at this result initially, just looking at the cover of this result, and you say, this is completely useless. I don't know what to do with this. It's not until we look at the isosurface when we start to get a little bit more information. So just like with the temperature result, I'm going to look at the isosurface to figure out what regions of my part I'm okay with having a little bit above the ejection temperature, and which parts I definitely want to have cooled down all the way. All right, so let's first of all start at our input. So let's start at our 5-second input. I can just type in 5 to our isosurface, and we can see how much of our material is cooled down at 5 seconds into the cooling cycle. So we can see that there's a few hot spots over here, the material right around our gate. That kind of makes sense. But there's also a lot of material in this. This is actually a thicker wall, and there's a lot of material over here. We really want to make sure that all of the main regions of our part are cooled down completely before trying to eject the part. So in this case, I would say that at 5 seconds, our part is not cooled down all the way. That's what I would expect. Our cooling time is only 5 seconds, which very rarely is it the case where your cooling time is going to be longer than your packing time. Actually, through the Excel file, we see that the packing time should be 5.25 seconds, and that would include the filling time. So it would be 5.25 minus the whatever filling time we used, which I believe was pretty quick. So it would be somewhere around like 5 seconds. So even if we were to use that ideal packing time, our cooling time is the same length as our packing time, which is very rarely the case. Most of the time, the cooling time is longer than the packing stage, just as a general stage of reference. So in this case, we can see that 5 seconds is definitely not sufficient to cool down our part completely. Now, keeping in mind that this is also based on the original packing time that we input, I can increase this slider to figure out when all of the main regions of my part are cooled down completely. Now, I could move this slider all the way until every element in my part is cooled down completely. So we can see that once this region down here cools down, I could technically say that that's when my part is completely cooled down to the ejection temperature. There's no chance of any sort of ejector pin penetration or anything like that. But this is 45 seconds. That's insanely long. I could inject probably 2 of these parts in that amount of time alone. So it's very important to note that we don't necessarily want all of the regions of our part down to the ejection temperature. We only want the main regions of the part. So I'm going to take this slider down a little bit until I'm left with only the hotspot regions. So in this case, I have a few hotspot regions. I have these 3 bosses here. I obviously have my gate. My gate is always going to be kind of a hotspot, quote unquote. I have this boss on the side, and then I have this guy down here. So you'll see that those are the first ones that show up. But once I start to see a main wall of my part show up, that's really where I want to stop adjusting my slider. So in this case, I would use, as an ideal cooling time, I would use about 15.6 seconds. Maybe you want to round it a little bit. You can reduce this even a little bit further. Obviously, the simulation is based on the size of the elements, so you can make some adjustments that way as well. But I would say that somewhere around like 15 seconds would be appropriate for this part. So just looking at that, if I were to look at that in comparison to what I had originally, where all of the regions of my part are cooled down, that's 45 seconds versus 15 seconds. That's a 3-fold decrease. So you can use this time to reach ejection temperature result really effectively to get an idea of when the part should be cooled down completely and when your cooling stage should finish. All right, and that's basically it. So the filling time can be optimized through that simple equation. You can use that to give you an input, and then you can look at the temperature to see whether you've balanced the shear heating versus the cooling effect through the center of the part. Then you can use the molten core result in the packing and also the part weight curve to figure out what your ideal packing time should be. And you can use this time to reach ejection temperature to optimize your cooling time. So this is the most effective way through simulation that you can optimize your cycle time going from simulation to reality, or even if you're already molding this part, you can simulate it and try to correlate it initially, and then from that correlation, you can make optimizations from there.
Thank you for watching the Moldex3D Advanced Tips and Tricks. Please don't forget to leave a like on the video if you enjoyed the content. If you'd like to suggest a future topic, feel free to let us know down in the comments. And finally, if you want to see more content like this in the future, don't forget to subscribe to our YouTube channel. Thank you for watching the Moldex3D Advanced Tips and Tricks, and go beyond simulation with Moldex3D.